Okay, graphing with rational functions today. Okay, so here what we have is we have a rational function. It's a rational function. It looks like a rational number, which looks like a fraction, right? Okay. So, when I have a rational function like this, it causes the graph to be, it doesn't have to be in two different places, but for this one it is. So both of these lines right here, or they're curved lines, are both part of this function. Does that make sense? So if I were to type this into GeoGebra, for instance, immediately you would get these two lines that pop up at the same time. Okay, that's the entire function, those two lines. The dotted line in the middle is called an asymptote. So let's not get ahead of ourselves. First, let's define rational function. So a rational function is something that looks like this. You've got something in the numerator and something in the denominator. Which reminds me, in the classes I was asking, P over Q. Where have we seen P over Q before? Other than the alphabet, Evan. We were putting it in a box. We were finding factors. Exactly. When we find factors, what are those?
When you intersect the X.
What do we call it when we intersect the X?
Y intersects it.
X intercepts or root, right?
There we go.
Okay. Not the squiggly line. When we had a long polynomial and we took the constant and we compared it to the first term or the coefficient of the first term, remember that?
No.
And we came up with a fraction, and that gave us our possible zeros or our possible roots. Remember that? Okay. All right, so an asymptote is a line that a graph approaches but never touches. So notice how there's an asymptote here, and the graph, it's approaching it, but it's never, ever going to touch it. As far as it's going to go up, it's never going to touch it. And down here, it's going to get closer and closer and closer and closer and closer, but it's never going to touch it. Okay? All right. Continuity. Just from looking at it, what do you think continuity means? Okay. Constant or continuous. So if I'm drawing a line and I'm continuously drawing, it means that it's traced with no breaks. So for instance, this line, this has continuity right here. This has continuity, but if you were to say both of them together, they don't, because you'd have to lift your pencil up to go to the next one, right? All right, so point discontinuity. What do you think that is?
The point where like the curve ends when like the curve in the middle.
Almost. Almost. We've seen it in one other thing that we've done, where we had holes, and they would break. Remember step functions?
Oh.
Remember those? That was point, well, it wasn't chapter 1, but that was point discontinuity. So it is a point that breaks continuity, that breaks the line up, breaks continuity. Hence, point discontinuity. I am going to demonstrate that. No. let's not be negative. What do you think the parent graph would look like? Okay, so everybody eyes up here. So if I tell you that this function of x over x minus 3 looks like this, where you've got these blue, right, these blue graphs here, and if I were to tell you, this time I'm really going to make it red, if I were to tell you that f of x equals 1 over x is my parent graph, what would that look like? Actually, you know what I'm going to do? I haven't done this in any of the other classes, but I want to make it pretty. You know me, this is my final product. Okay, so what would that look like? The dotted line would not be on -1, but you're right, it would shift. So if the dotted line is at x equals 3, what do you think the parent graph would be? Where do you think that dotted line would be? You're talking symmetry. Let's draw one at 1. Would it be there? Would it be over here? Where do you think it would be? -3, be here?
Wait, are you talking about 3 or 1?
This dotted line, right here. In general, a parent graph, it would be right at 0. Good job, Edwin. It would be right at 0. Right? For this one, it's shifted over a little bit. So if it was a parent graph, it would be right smack in the middle, right, with perfect symmetry. So what do you think these lines would look like, or these curves would look like? I keep saying lines. Good. Exactly. They can't ever touch it. They go right up against it, but they can never touch it. And you're going to find out exactly why in just a second. Okay? It'll make sense. All right, questions? You good so far? So this right here, I'm going to take this one, and this one, and this one. Is just like this, only shifted. See that? See how it's shifted? All right. Pencils down. So our first step is to factor. There's really nothing to factor. I hope you guys realize, right? You guys are laughing because, boy, about a week ago, no, I'm sorry, we were on break. Not just the one, oh, that one too, right? Most people would do that. I'm so glad you guys are laughing now, because you're right. So it's just nothing, right? They just cancel out. Now you understand how I felt when I graded those tests. Okay. All right, so there's nothing to factor, right? So our next step is to consider our limitations on our domain. So x minus 1 cannot be 0. Therefore, x cannot be what? Positive 1. And that is where we start talking about our asymptote. So where x equals 1, we have an asymptote. Our graph can never be x equals 1. Make sense? So we know from our parent graph that it should look probably something like that, only shifted over a little bit. Correct? So this is where the tedious part comes in. You ready, Jesus? Got it? That's all we can do. So we have an idea from the parent graph of where we need to start, but other than that, at this point, all we can do is just start substituting in values and getting numbers. Okay? So this isn't plugging and chugging, no. If we were to plug and chug, you would just, we wouldn't talk about asymptotes, we wouldn't talk about anything, we wouldn't talk about behavior of graphs. All we would do is start plugging in values and getting numbers, and we wouldn't have any direction. That's plugging and chugging. We have direction. right? Evan, where would you start? Since this is our asymptote, hi. Yes.
Sorry. They don't need any help.
Where would you start, Evan? At 2. So if you put in 2, you'd get 2 plus 1 divided by 2 minus 1, which is 3. So if I put in 2, I get 3. What would be the next one you'd pick?
4.
4. I don't have that one up here.
3.
Let's do 3. I would get 2. I'm going to go a little bit faster. So if I have 3, Brian, no writing. 3, 2. Starting to take some shape, right? Let's pick a larger number. How about 9? If I put in 9, I would get 10 over 8 or 1 1/4. All this can put in the calculator, right? But it does help to have an idea of what you're doing. So if I put in 9, I get 1 1/4. What do you see happening? No. It's curving, but it's getting really close. I don't think it's going to pass 1. I think it's just going to keep going on and on. And what about this way if I were to go up? It's just going to keep going right there. It's teasing you. All right, so there's part of it. All right, what would you put in next? I would put in 0. What would you get if you put in 0? -1. It's right there. If both of those were 0, right? Wouldn't it be 1 over -1? Kind of like doing that, right, Mo? He's not paying attention. Okay. 0, -1. Okay. If I'm going this way, it's never going to touch. Do I really need to put fractions in there? Nope. We just know it's going to go like this, correct? What if I go, what would you put in next? I don't need it. Thank you. -1. If you put in -1, you get 0. -1, 0. Let's pick another number. You want to put in -9? Okay, -9. If I put in -9, I get what do I get? You get -8 over -10, which is you guys are scaring me. Divide them both by 2. What do you get? 4 over 5. Good. So I would get, if I put in -9, I would get 4 over 5, which is not quite 1. What do you see happening here? If we go all the way out here, we're not quite to 1 here, but if we're going in the direction, we're not quite to 1 on this one. I don't think it's ever going to hit 1. Therefore, you probably have a vertical asymptote right there. See that? You try -100. Seriously, what would you get if you had -100? No. -100 plus 1 is -99 over -100 minus 1 is -101. Is it ever going to hit 1? 1,000. Jesus is going to try that theory out and get back to us. I'm saying it's never going to hit 1. Okay. All right, so let's look at our steps. Here's our steps. Factor. Didn't need to factor. Consider limitations on the domain. We did that. Are there any holes? We're going to talk about that next. Asymptotes. Drew our asymptote. Did a table. We have our graph. Questions? We base it on our asymptote. So since our asymptote, Jesus, was right here, I knew that this part of the graph is probably going to start over here somewhere. So I went real close to the asymptote in this direction, and then I go really close in the asymptote in that direction, and I work off of that.
Do we do the most stuff? Like, you don't use the Y, then we use the
I'm not quite getting the we started, here's the asymptote. Didn't we start at 2?
Yeah, I'm saying.
Then we went to 3.
You can do both of them.
You get the y when you plug the x in.
Yeah. I'm saying the line, if you know how you get x minus 1 can equal 0 and x can equal negative 1 is 1. Or 1 and 1. You get it, 1 and 1.
Okay, let's pause it for a second and explore what Janelle's saying, because I want to make sure that I understand. Okay, so I'm going to try another one. Pencils down again. All right, so this time I'm going to need to factor first. Okay? So I'm going to take this function and I'm going to factor it right over here. Evan, I can take that x plus 5 and put it in parentheses, right? Right? Okay. So let's factor this. This is really easy to factor because there's no coefficient in front, right? There's no leading coefficient. So x squared can only be factored as x times x, and negative 5 can only be factored as 5 and 1. This is positive 4 and negative 5, so one of them has to be positive, and one of them has to be negative. If you're still not getting that, you need to come get help with that, okay? All right, so we factored it. Let's consider limitations on our domain. In order to do that, Evelyn, what do I need to say can't be 0? Perfect. Or x plus 5 can't be 0, therefore x can't be negative 5. Perfect. So that is our asymptote, negative 5. Why does that not seem right to me right now? All right, no, we're gonna continue. Okay, there's our asymptote, correct? Okay, what am I forgetting over here? What other one? The other dotted line. Okay, remember we talked about, we aren't going to talk about the horizontal yet. Look at this right here. It's not simplified.
Oh,
right? The x plus 5, but it still matters, right? We still need this, only it's now not an asymptote. So I'm going to change the color of it. It's not an, and you're going to see why in just a second, why it's not an asymptote, but it still matters. Right, Janelle? Okay, so I changed it to red because it's really not part of my graph, but it still matters. Okay, so what is, when we're graphing, what does f of x stand for? Y. So isn't this just y equals x minus 1? What would x minus 1 look like? Y equals x minus 1. It's a line. Right? Isn't y equals, that's in slope-intercept form right there. Y equals mx plus b, that's a line. Specifically, let's talk about our parent graph first. Our parent graph is y equals x. What does y equals x minus 1 look like? Shifted down 1. Remember that? Behavior of graphs? If you didn't know that, though, let's just bring our line over here. We'll just put it behind for a second. Right there. I'll put it behind. It's hiding. Okay, so if I were to just graph that, how would I graph it? Where would I begin? Negative 1, begin with b, right? And we move, what's my slope? Up 1 over 1, up 1 over 1, up 1 over 1. You see that? Okay. Probably shouldn't have hit it. I'll bring it back forward again. So it looks just like that, correct? So what do you think that red dashed line tells us? There's a hole. right? There's a hole in our graph. There's a hole in our graph right there. What would that point be? If I were to put in -5 into my graph, what would that be? -5, -6. So at that ordered pair right there, there is a hole. That's what that signifies right there. Question? Yes, Evan? What do you do if there is a hole? You make sure you draw one so that you know there is a hole there. Yes, you put a line, then put a circle, then put a line, just like a step function, right? Step functions look like this, where you have a hole, then a line, then a dot, then a hole, then a line, then a dot, right? This is the same type of thing, only I just didn't want to break up my lines there. All right, go ahead and copy that down. All right, why don't you guys try this one on your own? At least get to the point where you're about to graph it. So go ahead and factor this one for me. Okay, so let's factor this. I have f of x equals, how about, Raymond, what did you get for the numerator? What do we call that, Raymond? Not other one. Difference of two. Perfect square is the other one where they're both perfectly the same. Difference of two squares when they're different. Okay, so difference of two squares. And then in the denominator, Janelle, what did you get? X minus 5, x minus 1. Perfect. Before I simplify, I need to consider the limitations on my domain. So, how about Nicole? Nicole, what can x not be? Okay, right here, it is -1. Here, let's start here. So x minus 1, you got it? Did you catch it? Okay, so what can x not be? It can't be 5, or 1. Do you see why it's not -1? Because it is -1 here. If I were to say x minus 1 can't be 0, and I add 1 to both sides, x cannot equal +1. Got it? Because if it was +1, you get 1 minus 1 and not 0. Okay? All right, so we figured out that x can't be 5 and x can't be 1. I'm just going to go ahead and draw these 1 and 5. Asymptotes, right? Mo's already on to me. Okay, Mo, what do I need to do still? What happens when I cancel out a factor that originally was one of the ones that restricts my domain? What happens then? It becomes a hole. No, x minus 1, that's where my hole is, right there. I'm going to change the color. You see that, Evan? Because it goes away, it creates a hole somewhere on that line right there. It's not an asymptote. Somewhere, because that's the one that got canceled out. X minus 1 got canceled out. When we found x minus 1, it makes, got it?
So it'll be a curve with a hole.
It'll be a curve with a hole in it. Good job.
Yeah.
You got it. Okay, let's continue. All right, so this one's for Evan. I think it was Evan that asked. No, it was Jesus. Jesus, now we've got, this is the one we're going to work off of, right here. That's our asymptote. So where do we begin? What's the first value you would plug in, based on the fact that you got an asymptote right here? 4 would be a good place to start. So if I plug in 4, I've got numbers here. If I plug in 4, I get -5. 4, -5, right there. What would you plug in next? 2. Plug in 2, you get -1. So what's happening to this? Starting to curve, right? What else? Let's pick one more. I would put 0. Try 0. What happens if you put 0 in? Oh, by the way, Mrs. Watkins brought this to my attention. You don't have to plug it into this original. You can just plug it in here. I'm so glad you guys are so much smarter than me. You guys are. So you guys teach me stuff all the time. Okay.
So you plug it into the...
This one. It's simplified. These are the same, right? Only this one's just in simpler form. So use the one that's in simpler form.
The x minus 1.
Nope. This right here. Use that right there. Okay? So if you plug in 0, you get what? Negative 1/5. So if I plug in 0, I get negative 1/5, which is like right there. Correct? So it's curving like this? I don't think we need to. It's curving just like that. Only what? Mitchell, only what? There's a hole right here. Now that we have a hole right there, can I erase that red line? Don't need it anymore. It still matters. Right? It can go away. We don't need it. There's a hole there. It was just like a place marker to find our hole. Okay, are we good? Well, you need to find the hole. Yeah, it just guides you. It just...
Well, the line always crosses the hole, the curved line that always crosses.
That's the only place the hole is.
If there's a hole, long line will cross the hole.
Exactly. Make sense? Okay, but we're not done, Jesus. Which way do we need to go now? On the other side of the asymptote. So we're going to go to 6, right? Do you see that? You see how it kind of guides us? We know that our graph is going to come right up against that asymptote. So we need to go on the other side of the asymptote and see if there's anything over there as well. So let's go to 6 and see what we find. If I go to 6, I get 7. Right here. 8, what do you get? What? 8, you get 3. So what's happening now? Somebody put in 10, what do you get? What do you get if you put in 10? 10 plus 1 is 11. 10 minus 5 is 5. So what's 11/5? 2 1/5? Right? Surprised you guys haven't pulled out calculators. 2 1/5, about right there. That makes sense, right? It's curving like that. There's your graph. No, it's not hard. What is it?
Tedious.
Tedious. Not hard. There's just a lot of steps to it. He's just horizontal one. Today you don't have to do the horizontal one. Okay, we were just using it to guide. I was using it to show you symmetry. Right? I wouldn't say it's right there, right? Wouldn't it be down a little bit? Probably right there. Right there. Right here. Right here. Okay. So, freeze. What did you learn today? Graphing is tedious. Besides graphing is tedious. I said to freeze, guys. Graphing rational functions. What happens, listen up, what happens when a factor that determines an excluded value is simplified to 1? There's a hole. Good. On your assignment sheet, let's look at this one, guys. What are the excluded values of this rational function? 1 and negative 3. So what might asymptotes be? X equals 1 and x equals negative 3. None of them cancel, so neither of these are holes. So then what happens? Is this going to give me a graph? Because I did copy one. No. I want a graph. Oh, well. So what would this look like? I need a graph, because this is my good one. Give me a second, guys. Okay, guys, this is what's going to be on your homework, so I want you to see it. Let's see what this would look like. Okay, so if these are my asymptotes, one's at x equals 1, and one of them's at x equals -3, that means these asymptotes are affecting my graph. Alright, so maybe it looks like this, but then there's something inside here. Well, it's going to go like, if it was looking like this, then it would come up, but then this side would make it come back down.
Yeah. So there has to be something in there?
No holes.
Never.
See what I mean?
I didn't know there's one inside.
Okay, so you would put in, plug in 0, and you would get a point. Then you plug in -1, and you get a point. You plug in -2, and you get a point. Then you'd say, okay, it's curving down. Then you put in -4, and you get a point, and you keep seeing what the behavior of the graph is going to be, right? But if there's 2 vertical asymptotes, you know there's something funky going on with this graph than just a regular parent graph. Yes? Yes. Okay, there will be one on the homework. Let's get to that. What would be other possibilities? What about this one? You're going to have to graph the rational function, and in order to graph it, you're going to have to plug in values and see what happens. I'm telling you, if you have a vertical asymptote and you started to graph this, it would come around and would start to go this way, and that makes sense because it can't. Check this out. If this were to start going like this, it can't touch that, right, Evan? It would have to be forced back up because it can never touch the asymptote. Does that make sense why it makes a little turn like that? Okay. So I'm going to redraw this. It was a good lesson? You understood it? Good. Thank you. All right. We're good. Let's do some homework.